Proton NMR spectroscopy. Let's begin by introducing you to a quite unusual term, but an important term in the context of NMR spectroscopy, precession, or to precess. You see here that precession is a change in the orientation of the rotational axis of a rotating body. And I've simulated here a spinning top. You can see that as well as spinning, the angle of the axis of rotation keeps changing as well. The subatomic particles in an atom, that's protons, neutrons and electrons, can also be imagined as spinning on their axes. And this spinning action gives them a so-called magnetic moment. We'll be looking at the protons and neutrons in the nucleus, collectively known as the nucleons. The spins of the nucleons in atoms are found paired against each other, so that where you have a nucleus with an even number of nucleons, then the spins cancel and the nucleus has no net spin, no net magnetic moment. But where the number is odd, then it does have net spin, and such a nucleus will have a net magnetic moment and will be useful for identification purposes in NMR spectroscopy. So let's consider a few examples to illustrate this point. We'll begin with hydrogen. This is what hydrogen is like. It's got one proton, no neutrons, so it has a net spin, a net magnetic moment. Next, deuterium. This is it. One proton, one neutron. Spins cancel, so it has no net spin, no net magnetic moment. Here is an atom that we don't come across, two protons and one neutron. Such an atom would be helium. That's what we expect of helium normally, two of each. Spins cancel, no net spin, no net magnetic moment. Here is an atom with three protons and two neutrons. It would have a net spin. But once we have three protons and three neutrons, the spins cancel, so no net spin in that nucleus. Not useful for NMR purposes. And there's C12 and C13. In C12, the spins cancel. In C13, they don't. So C13, like H1, is used in NMR spectroscopy. I'm going to use this animation to represent how the proton both spins and precesses about that axis there, marked in blue, within the nucleus of an atom. It's perhaps difficult to see it change the angle of its axis, but as it does so, the arrowhead changes its direction from north to south. In the absence of a magnetic field, you can see here that these two different orientations are of equal energy. However, once an external magnetic field is applied, these two will split into separate levels. The ones that align with the magnetic field will be in a lower energy state, and they're assigned m equals half. Those that are aligned against the magnetic field will be at a higher level, given the value m equals minus a half. So you've got spin states plus a half and minus a half. And as you see there, due to thermodynamic considerations, one will always have slightly more nuclei in the lower level. Note that the gap in these energy levels is tiny. The stronger the external magnetic field, the bigger the gap. But even in a very powerful magnetic field, the gap in the energy levels is minuscule. And the energy of that corresponds to the energy of radio waves. You see what's happening here with energy of the right wavelength, somewhere within the radio part of the electromagnetic spectrum. We get, as you see here, a proton changing its orientation, changing its spin so it goes from with the magnetic field to against the magnetic field. What's important in NMR spectroscopy, producing the peaks in the NMR spectrum, is what's happening here. It's when that proton returns to the lower level, it reverses its spin again, so that its spin is in line with the external magnetic field. And of course, as it drops down, it will give out energy, and a receiver will pick that up, and that will then be sent to the recorder. Working with computers, we sometimes talk about toggling back and forth. The term used here is resonance, to move back and forth between those two different states. And so the peaks are referred to as resonances. And the more of that kind of activity taking place, then the bigger the peaks in the NMR spectrum. Let's then take a look inside one of these NMR spectrometers to see what goes on. Highlighted in blue there, that's where the sample will be placed, and will be subjected to two things: an external magnetic field and to waves, radio waves broadcast from a transmitter there on the top left. Highlighted there in blue then is the transmitter that broadcasts a fixed radio frequency. What changes is the strength of the magnetic field. You'll see the blue arrowhead flipping back and forth, at times in line with the magnetic field and at times opposed to it. You'll notice now that when the arrow flips from being against the magnetic field to with the magnetic field, in other words from pointing down to pointing up, and that represents the proton changing from the higher energy spin state to the lower energy spin state, and that will give out energy in the form of electromagnetic waves with a wavelength corresponding to radio waves. So that's picked up by the radio frequency receiver there in the bottom left, and that will be sent to the recorder, where it will give results on the y-axis determining the heights of the peaks, or more accurately or precisely the area under the peaks. And over the far right there you can see that what's actually happening is that the NMR spectrometer sweeps the magnetic field. So it strengthens the magnetic field, and in turn each different type of proton, depending on the particular strength of magnetic field that it experiences, will begin to oscillate back and forth. And the more protons of a particular type that you have in that particular region, then the stronger the signal, the bigger the peak, or the greater the area under the peak. Now we get to the nitty-gritty of NMR spectrometry. Let's consider why protons in different parts of the same molecule within the same magnetic field experience a different strength of magnetic field and require a different amount of energy to bring about resonance. Take a look at the two asterisks here, which represent a bonding pair of electrons between the hydrogen, because we're looking here at hydrogen or proton NMR. So between hydrogen and typically carbon or oxygen or halogen or perhaps nitrogen. Now hydrogen is low in electronegativity, so when it's bonded to a carbon atom or chlorine atom or oxygen or nitrogen atom, the other atom will be more electronegative and by definition will have a greater pull on the bonding pair of electrons. So depending on how electronegative it is, that bonding pair of electrons will be drawn further and further away from the hydrogen nucleus. And this is the single most important point to be made about the NMR spectrometer. This is how it discriminates between different proton environments within an organic molecule. Because the further those electrons are pulled away from the hydrogen, the more it's exposed to the effects of the external magnetic field. The term de-shielding is used because those electrons help to shield the proton from the influence of the external magnetic field. So as they are pulled further and further away by increasingly electronegative groups, then we get less shielding. We get what's called increased de-shielding. So now we have the most important points about NMR spectroscopy, namely that protons with maximum de-shielding experience the strength of the external magnetic field the strongest, and therefore will begin to resonate in a relatively weak external magnetic field.
NMR spectroscopy has become one of the most frequently used analytical tools to elucidate chemical structure. It is particularly useful for carbon-based chemical compounds, also known as organic compounds, the molecules that make up all living things, and many substances that we interact with on a daily basis. In this video, we'll take a look at how NMR spectroscopy works and provide a visual metaphor for what is happening at the nuclear level. If we consider a chemical compound, we are particularly interested in what atoms are present and what the arrangement of those atoms are. If we were able to look inside an atom, we'd see a dense and positively charged nucleus. It is the nucleus that NMR spectroscopy detects and gives us a lot of information about the overall structure of the molecule. Here's how it works. Ordinarily, nuclei are oriented randomly, but if we place a sample of a chemical compound in a strong magnetic field at the heart of the NMR instrument, the nuclei line up like a compass needle aligning in a magnetic field and start to precess like a spinning top as it spins on a table. Eventually, the magnetic field, designated B0, is oriented along the z-axis. Different nuclei have different spins, and the ones with spin 1/2 can exist in one of two possible spin states. These include the following atomic isotopes. The hydrogen nucleus, usually referred to as simply the proton, is present in almost all organic compounds and is the one most frequently analyzed by NMR. The precession frequency, or Larmor frequency, is given by the following equation and is dependent on the strength of the magnetic field and the gyromagnetic ratio, which is a constant for a given isotope. If we apply now a short radio frequency pulse, or RF pulse, at right angles to B0, the nuclei will flip down to the XY plane in unison and continue to precess. Let's represent the average magnetic moment of a set of nuclei by this sphere. At equilibrium, the magnetization vector will be aligned along B0 as depicted here. As we've seen, the RF pulse will flip the magnetization vector to the XY plane. The rotating magnetization vector induces a current in a receiver coil. This signal is detected and amplified. We can see that the oscillating signal sweeps out a sine wave with decreasing magnitude as the nucleus realigns with the magnetic field B0. This wave is called the free induction decay, or FID.
I'm going to take ethanol as my first example here, C2H5OH, and the asterisks represent the valence electrons of the atoms. Highlighted here on the right, look what happens to the bonding pair of electrons between the O and the H. Oxygen is the second most electronegative element after fluorine. Being very strongly electronegative, you see it has pulled the bonding pair of electrons very close to it and well away from the hydrogen that's attached to it. So de-shielding is very high there. Now take a look at the other electrons to the left of that oxygen, the electrons shared between the carbon and the oxygen atom. Again, oxygen is more electronegative than the carbon atom, so it will win out and pull the electrons closer to it. So that causes that particular carbon to become, as it were, greedier for the electrons it's sharing with the two hydrogens above and below there. So in this animation, I'm pulling the electrons in even closer to that carbon than would normally be the case if that oxygen wasn't present. So it has a knock-on effect on those hydrogens or protons coloured blue. They will be de-shielded more as a result.
Here we have a rotating sphere of water about 25 millimeters in diameter, and inside this sphere are a whole bunch of little tiny air bubbles. And we will see what the angular acceleration due to rotation does to these air bubbles as a function of time. What you are observing are the bubbles moving to the center axis of rotation. As a function of time, they will form this rather tightly packed bubble core.
To me, it's beautiful. That's why I actually have a printout of this, because this simplex picture, for example, it would take a long time to explain, and yet it's so fundamentally beautiful. We actually have the egg shape of the golden ratio around the magnet. We have the structured distilled water, and we actually have, it looks like a rocket ship, you know, it's blasting off the surface, but there's an explanation for that. And we have this ethereal wispy banding around the plane of inertia. And also, too, very fascinating. If I did not have this magnet in here and I just put the exact same vessel with the exact same distilled structured water in it, it would freeze not too long after, you know, the outside had frozen. I mean, it literally takes 3 to 4 times as long to actually freeze the center section around the magnetic field. And that actually, the implications of that are fascinating. There'll be future patents based upon the fact that you can keep water. Well, you could do that by adding salt, but what if by simply using a powerful magnetic field from a permanent magnet, you can keep water from freezing and crystallizing far, far longer? The implications of that for patents and inventions are actually far-reaching. Far-reaching.
And the carbon there to the left of that carbon will also be influenced. It will have bonding pair of electrons between the two carbons pulled slightly away from it, so there's a knock-on effect for it as well. In turn, that carbon will become greedier for the bonding pairs of electrons it shares with those 3 protons. So those 3 protons will be deshielded a little bit more as well, not by as much as those in blue in the middle, but nevertheless deshielded more. So the knock-on effect goes right along the molecule. So here you see the magnetic field. These particular protons, of the 3 types of protons in ethanol, will experience the most shielding. That's to say, they have the least deshielding. And therefore will feel the strength of the magnetic field, the external magnetic field, on its weakness. Those in the middle have been deshielded less than the proton there in green attached to the oxygen directly. But they will experience a stronger magnetic field than the protons on the carbon to the left, because deshielding has been greater. And there on the right then, hydrogen or proton attached directly to the electronegative oxygen atom, that will have the most deshielding and will experience the strength of the external magnetic field the strongest. Let's now take a look at the accepted internal standard used in both proton and C13 NMR spectroscopy. This is it here, TMS, tetramethylsilane. You can see it's a silicon surrounded by 4 methyl groups. So in this molecule you have got 4 times 3, that's 12 protons that are all in the same environment, referred to as equivalent protons. Somewhat unusually here, carbon is bonded to an atom in silicon that is less electronegative than it. That means that the bonding pairs of electrons there between the carbons and the silicon are polar in favour of the carbon. So in this particular case, the carbon is going to be less greedy for the bonding pairs of electrons between it and the H atoms in the methyl groups. Why? Again, it's because in this case the carbon is more electronegative than the silicon. So the bonding pair of electrons between the carbon and the silicon will be a little closer to the carbon, and that makes it less greedy for the electron pairs that it shares with the protons, the hydrogens around it. So in this particular case, the bonding pairs of electrons are unusually close to the protons, these 12 equivalent protons. So this is an example of a molecule where the protons have maximum shielding or minimal de-shielding. So we're now ready to move on and take a look at some of these NMR spectra, and I'll begin with the NMR spectrum of ethanol. Note that on the x-axis we have the so-called chemical shift, given the symbol lowercase delta, and it's measured in ppm, parts per million. If there is a peak for TMS, it'll appear at 0 parts per million. And for example, if you have a peak at 5 parts per million, that means that the protons producing that peak require a magnetic field 5 millionths less than the protons found in TMS. So the strength of the radio frequency is maintained at a constant value, and the magnetic field is weakened as we progress from right to left. If TMS does produce a peak, and you won't always find a peak for TMS on these spectra, it'll occur there at 0.0 parts per million. As we weaken the magnetic field, the methyl protons there, now highlighted in black, they have the most shielding, the least amount of de-shielding in this ethanol molecule, and they will produce a peak at the strongest magnetic field there, just below 1 parts per million. Next we'll have the methylene protons in the middle, and they produce a peak around about here, just past about 3.5. And then you have the proton attached directly to the O, which has the highest amount of de-shielding and therefore experiences the strength of the external magnetic field at its strongest. It forms a peak there at around about 4.75. And I'm afraid that peak for the proton attached to the O is sometimes shown in spectra appearing between the other two peaks, and that would have to be down to some change in conditions such as the solvent or the purity of the ethanol sample. We have both low resolution and high resolution NMR spectroscopy. To begin with, I'm looking here at low resolution NMR. The area under the NMR resonances, these peaks, is proportional to the number of hydrogens which that resonance represents. In other words, the number of different hydrogens or protons in these different environments. It would be difficult, of course, to work out the area under these peaks. So instead, the NMR spectrometer uses a process of integration to produce, as you see in this red line, an integration trace. And you'll see how that can be used to get the ratio of protons in the different environments. So as we move on here with this red line representing the integration trace, watch what happens next. It's the height of the steps that's important. So instead of comparing the areas under the graphs, this next peak here, you'll see that the drop is smaller because the peak or the area under that peak is smaller than the one highlighted in yellow. As we move on then to the last peak, for the proton attached to the O, it's smaller again. So instead of measuring the areas under the peaks, we simply measure the heights in the integration trace. And if we compare the heights, then we get the ratio of the protons in the different environments. So apart from the peak for TMS, we have 3 peaks, and in the integration trace we have 3 drops. In the ratio 3 to 2 to 1 in terms of their heights. So that first peak is for TMS. The second peak there is for the methyl protons, 3 protons in that region, 3 equivalent protons. The next peak is for the methylene protons. We've got 2 protons in that environment, 2 equivalent protons. And then the last one is for the proton of the OH group, and we've just 1 unique proton in that environment in the molecule. Now we can take a look at high resolution NMR spectroscopy, which includes so-called spin-spin coupling. This results because of interactions between the magnetic moments of adjacent protons. Let's see how this works. We'll begin by taking a look at the peak produced by the methyl protons there on the left. Let's consider what constitutes adjacent protons to these particular protons of the CH3 group. Well, this is how it works. Look at that carbon with the green arrow pointing at it. That's the carbon that's holding these methyl protons. Now, any protons attached to an atom that is in turn attached to that carbon would be considered adjacent protons. So these 2 protons here of the methylene group would be considered adjacent protons to the protons of the methyl group. I'd like to show you that there are 4 different possible spin states here. The first combination would be that both protons are aligned opposing the external magnetic field like this. They will have the effect of weakening the strength of the external magnetic field experienced by the methyl protons there on the left. This is another possible combination where both spins are in line with the magnetic field, and as you'd expect, they would strengthen the magnetic field that is experienced by the methyl protons. Then you could have this possibility where one is with and the other is against the external magnetic field, and of course they will cancel one another's effect. And you could have the reverse of that, but again these are opposing one another and cancel. Look at the ratio of these possibilities. They are 1 to 2 to 1. So 4 possibilities. 2 of the 4 have no effect on the peak, and the other 2 have opposite effects, one weakening and the other strengthening. So we're going to get the peak split into 3 sub-peaks. So there in the middle you have the original peak, and the area under that peak will be twice the area under the peaks either side, reflecting the ratio 1 to 2 to 1. And this peak to the right, or sub-peak, which will represent a smaller chemical shift, has been produced as a result of the adjacent protons that are paired and opposed, therefore weakening the effect of the external magnetic field, so that a somewhat stronger magnetic field is required to bring about resonance. And this other sub-peak, which is further downfield, it has got a greater chemical shift. It's caused by the adjacent protons that are paired and in line with the magnetic field, making it stronger, so that the strength of the magnetic field needs to be weaker in order to bring the protons into resonance. And as you see, that's referred to as a triplet, and the sub-peaks are in the ratio 1 to 2 to 1. Okay, let's now do it the other way around. Let's consider what happens to the peak for the methylene protons there in the middle as a result of the adjacent protons. Now, again, this is a carbon we have to consider, to which the methylene protons are attached. Our job then is to take a look to see if there are any protons on the atoms adjacent to that carbon. That oxygen does have a proton, but for reasons I'll explain in a moment, that proton does not influence the peak. However, this carbon here to the left has got 3 protons attached, and let's take a look at the possible orientations or the possible spin combinations of these 3 protons of the methyl group. So there's the first combination where the magnetic moments of all 3 protons are aligned with the external magnetic field. Here's a second possibility, the opposite, all 3 aligned against. Here's a third possibility, the top one's pointing down, the other 2 are up. Here the bottom one is down, the other 2 are up. It's effectively the same as the previous one. The net effect is 1 up. Like so. And then you could have the one at the side pointing down and the other 2 up. Again, the net effect is 1 up because we have 2 that cancel one another. And then we could have the converse case where the net effect is 1 down. You can see there the 2 sets to the left have a net effect of supporting or strengthening the external magnetic field because they're in line with it. As a result, the adjacent protons will require a weaker magnetic field to bring them into resonance, and then the 2 sets to the right, the converse case holds. The ratio you see is 1 to 3 to 3 to 1, and that's reflected in the areas under the sub-peaks of what's called a quartet. Moving on then to the last proton, the proton attached directly to oxygen in the hydroxyl group. This peak is not split in high resolution NMR spectroscopy. It appears as a singlet, so-called singlet. This is because ethanol has acidic properties, and there's a dynamic equilibrium where that OH bond is constantly breaking and forming. In other words, the hydrogen goes off as a proton and then comes back again. And so it's said that the proton in this case doesn't stay around long enough for either it to cause splitting of adjacent protons or for adjacent protons to cause its peak to split. And you'd be glad to know that it's not necessary to use statistics to work out the number of permutations when it comes to spin-spin coupling. You can use the so-called n+1 rule, where n equals the number of adjacent protons, to calculate the number of sub-peaks that will be produced. And you'll see that illustrated in these examples. I'm going to take a look at 2 different esters that can be formed from this formula, C4H8O2. And here they are, methyl propanoate and propyl methanoate. These will give completely different NMR spectra. In fact, even the number of peaks in their 2 NMR spectra will be different. So let's consider the number of peaks and as well consider spin-spin splitting of those peaks. So let's begin with the top ester, methyl propanoate. Look at the CH3 group there at the top right. How many adjacent protons has it got? Well, it has protons there on the CH2 group, so 2 adjacent protons. Use n+1, that gives you 2 + 1 is 3, so that peak for the methyl group will be split into a triplet. Moving on to the CH2 adjacent, it's got 3 protons on the carbon to the left, none to the right, so 3 + 1 is 4, it'll be split into a quartet. And that leaves just one other set of protons down there in the CH3 group, and they have no adjacent protons. As you can see there are no protons on adjacent atoms, so that will remain a singlet. Down now to propyl methanoate. That hydrogen there, well, the carbon it's attached to is not attached to any atoms that are directly attached to protons, so that'll give us a singlet. That CH2 there, well, none to the left, but to the right it has 2 adjacent protons. It will form a triplet. Now the next carbon has a lot of adjacent protons. It's got 2 on the carbon to the left of it and 3 on the carbon to the right of it, so that's 2 and 3 is 5. Put 5 into the n+1 rule and you get 6. That will be split into a sextet, it's called. And the CH3 there has got 2 adjacent protons, so that'll give us a triplet. Let's then take a look at the NMR spectrum for the one at the top, methyl propanoate. You recall that it had 3 different types of proton. That singlet there is produced by the CH3 attached directly to the O. It will have the maximum amount of de-shielding and will appear furthest downfield with the largest chemical shift value. Remember, we're comparing the proton environments with TMS, and the proton environment of these protons in this CH3 group is the most different when compared with TMS. Okay, and then we have the CH2 there in the middle with 3 adjacent protons producing a quartet, and there you have it, in the ratio 1 to 3 to 1, remember. And then lastly, furthest away from the electronegative groups, and therefore with the least de-shielding, you've got the CH3 group on the extreme left. So it's got the lowest chemical shift, and with 2 adjacent protons there on the CH2 group, it's split into a triplet. So with methyl propanoate, there are 3 peaks. When we look at propyl methanoate, we'll see that there are 4 peaks. And the pattern of splitting here is a singlet, a quartet, and a triplet. Let's just put that together in one diagram then, and this is what we've got. You might consider to pause here and take some effort to associate each of the different types of proton in methyl propanoate with each of these different peaks, and come to understand why the peaks are split in the way they are split because of the number of adjacent protons. Okay, so let's look now at the other isomer, propyl methanoate, also known as propyl acetate. So we're going to find here that we have not 3 but 4 different peaks. So if we trace out the high resolution NMR spectrum, we get a triplet, we get a sextet, we get a singlet, and we get another triplet there at the end at around 4 parts per million. The triplet furthest downfield is produced by that CH2 group because A, it's got 2 adjacent protons, and B, it's attached directly to the electronegative oxygen. That CH2 group has got 5 adjacent protons, n plus 1 gives 6, so it's split into a sextet. I've left out the singlet there, I'm afraid. That's the H attached to the COO. And then you've got a triplet produced by that CH3 group, which has 2 adjacent protons. So 4 peaks, 2 triplets, a singlet, and a sextet. That's my look at NMR spectroscopy. Thanks for listening.